The next topic is periodic analog signals. Periodic analog signal can be classified as simple or composite. A simple periodic analog signal, a sine wave, can't be decomposed into simpler signals. A composite periodic analog signal is composed of multiple sine waves. Sine wave. The sine wave is the most fundamental form of a periodic analog signal. When we visualize it as a simple oscillating curve, its change over the course of a cycle is smooth and consistent, a continuous rolling flow. Figure 3.2 shows a sine wave. Each cycle consists of single arc above the time axis followed by a single arc below it. Sine wave. A sine wave can be represented by the three parameters: the peak amplitude, the frequency, and the phase. These three parameters fully describe a sine wave. Peak amplitude. The peak amplitude of a signal is the absolute value of its highest intensity proportional to the energy it carries. For electric signals, peak amplitude is normally measured in volts. Figure 3.3 shows two signals and their peak amplitudes. Example 3.1. The power in your house can be represented by a sine wave with a peak amplitude of 155 to 170 V. However, it is common knowledge that the voltage of the power in US homes is 110 to 120 V. Two signals with the same frequency and phase but different amplitudes. This discrepancy is due to the fact that these are the root mean square values. The signal is squared and then the average amplitude is calculated. The peak value is equal to 2 raised to the power half into RMS value. Example 3.2. The voltage of battery is a constant. This constant value can be considered a sine wave. As we will see later, for example, the peak value of an AA battery is normally 1.5 V. Period and frequency. Period refers to the amount of time in second a signal needs to complete one cycle. Frequency refers to the number of periods in 1 second. Note that the period and frequency are just one characteristic defined in two ways. Period is the inverse of frequency and frequency is the inverse of period, as the following formulas. Frequency and period are the inverse of each other. Two signals with the same amplitude and phase but different frequencies. Period is formally expressed in seconds. Frequency is formally expressed in hertz, which is cycle per second. Units of the period and frequency are shown here. More about frequency. We already know that frequency is the relationship of a signal to time and the frequency of a wave is the number of cycles it completes in 1 second. But another way to look at the frequency is as measurement of the rate of change. Electromagnetic signals are oscillating waveforms. This is, they fluctuate continuously and unpredictably above and below a mean energy level. A 40 Hz signal has one half the frequency of an 80 Hz signal. It completes one cycle in twice the time of the 80 Hz signal. So each cycle takes twice as long to change from its lowest to its highest voltage levels. Frequency, therefore, though described in cycle per second, is a general measurement of the rate change of a signal with respect to the time. Frequency is the range of change with respect to time. Frequency is the rate of change with respect to time. Change in short span of time means high frequency. Change over a long span of time means low frequency. If the value of a signal changes over a very short span of time, its frequency is high. If it changes over a long span of time, its frequency is low. To two extremes. What if a signal does not change at all? What if it maintains a constant voltage level for the entire time it is active? In such a case, its frequency is zero. Conceptually, this idea is a simple one. If a signal does not change at all, it never completes a cycle, so its frequency is 0 Hz. But what if a signal changes continuously? What if it jumps from one level to another in no time? Then its frequency is infinite. In other words, when a signal changes instantaneously, its period is zero. Since frequency is the inverse of period, in this case the frequency is 1 by 0 or infinite, unbounded. If a signal does not change at all, its frequency is zero. If a signal changes instantaneously, its frequency is infinite. Phase. The term phase describes the position of the waveform relative to time zero. If we think of the wave as something that can be shifted backward or forward along the time axis, phase describes the amount of that shift. It indicates the status of the first cycle. Phase describes the position of the waveform related to time zero. Phase is measured in degree or radius. That is, 1 degree is 2 pi by 360 radian and 1 radian is 360 by 2 pi. A phase shift of 360 degree corresponds to a shift of a complete period. A phase shift of 180 degree corresponds to a shift of one half of a period, and a phase shift of 90 degree corresponds to a shift of the 1/4 of a period. Three sine waves with the same amplitude and frequency but different phases. Looking at figure, a sine wave with a phase of 0 degree start at time 0 with a 0 amplitude. The amplitude is increasing. Second, the sine wave with a phase of 90 degrees starts at time 0 with peak amplitude and the amplitude is decreasing. Third, a sine wave with a phase of 180 degrees starts at time 0 with a 0 amplitude. The amplitude is decreasing. Another way to look at the phase is in terms of shift or offset. We can say that first, a sine wave with a phase of 0 degree is not shifted. Second, a sine wave with a phase of 90 degree is shifted to the left by 1/4th cycle. However, note that the signal does not really exist before time 0. Third, a sine wave with a phase of 180 degree is shifted to the left side by 1/2 cycle. However, note that the signal does not really exist before time 0. Wavelength. Wavelength is another characteristic of a signal traveling through a transmission medium. Wavelength binds the period or the frequency of a simple sine wave to the propagation speed of the medium. Wavelength and period. While the frequency of a signal is independent of the medium, the wavelength depends on the both frequency and medium. Wavelength is a property of any type of signal. In data communication, we often use wavelength to describe the transmission of light in an optical fiber. The wavelength of the distance a simple signal can travel in one period. Wavelength can be calculated if one is given the propagation speed and the period of the signal. However, since period and frequency are related to each other, if we represent wavelength by lambda, propagation speed by c, and frequency by f, wavelength equals to propagation speed into frequency equals to propagation speed by frequency. The propagation speed of an electromagnetic signal depends on the medium and on the frequency of the signal. For example, in a vacuum, light is propagated with a speed of 3 into 10 raised to the power 8 m by s. That speed is lower in air or even lower in cable. The wavelength is normally measured in micrometers instead of meters. For example, the wavelength of red light is 4 into 10 raised to the power 14 in air is 0.75 mu m. In a coaxial or fiber optical cable. However, the wavelength is shorter because the propagation speed in the cable is decreased. Thanks for watching this video. If you found this video helpful and want more videos like this, then please let me know by click on like button and subscribe to my channel. Thank you.